Greetings and welcome once again to my new calculus channel. My name is John Gabriel, and I'm continuing from where I left off in the previous video. That is, I talked about Euclid's proposition 1 in book 1 and showed you that the proposition is quite simple and relies on the symmetry of that geometric object known as a circle. Now, just to quickly revise, remember that you cannot have any other geometric object more complicated or more complex geometric object than the circle without defining it using the circle. So for example, you have no triangles or pentagons or anything else unless you define angle, and for that you need the circle. So I hope I've made that clear. Also, I hope I've made clear to you that you cannot call a period a point. It's just a visualization of a point. So this little dot here is not a point, it's just a visualization. This the so-called line here that you see here, and the so-called line that you see here, the bottom, is not a straight line. It's a visualization of a straight line, which means that we're considering the distance. Okay, so in Euclid's Elements, we're dealing with abstract objects, not things that you can draw, even though it says that let us draw a circle or a straight line. We're doing that only to communicate the perfect ideas that are found in Elements and that are entirely Platonic. Okay? In other words, anyone who's smart enough can realize these ideas. So book 2 in proposition 1 says to place a straight line equal to a given straight line at a given point. Now again, Euclid's so-called proof is very obfuscated, and I'm going to show you a shorter way based on the fact that there should have been a prologue to the Elements, and this is the prologue, this article here, which I shall place a link to in the details section. Okay. It takes about 12 pages before you can even get to the definition or the derivation of a circle. And I start in this prologue with nothing. It's it is one of the most important documents written in the last 2,700 years. And it has also been translated into Greek. You can find both those links in the details section of my previous video. Now, let's begin with this proposition. So first of all, to correct Thomas Heith, it's blatantly false that the proposition admits of a number of different cases because it handles every single one of them. In other words, it's generic. So Thomas Heith's remark here about Euclid invariably considering only one particular case, usually the most difficult, is false. All right? So let's go to the proposition. So what they're telling you is, what Euclid is telling you is, if you have a point, let's say point A, and any line segment from B to C, and it doesn't matter where it is, as I'll show you in a moment, you can construct another line segment, AL, which is exactly equal to it. All right? So the constructions are as follows. Okay, those blue dotted lines are the constructions. First, you construct the equilateral triangle, which is DAB, right? And then you will construct, after that, the circle around B, which is this circle, and finally, the circle around D. And the proof is that Euclid produces a circle with radius equal to the sum of the given line, this sum of this given line, which is equal to this line here, and a side of the quadrilateral, this side of the quadrilateral angle. Okay, so in other words, what you're really looking at is that the new line, this AL, is equal to the radius of the circle D, the radius of the whole circle D, minus the side of the quadrilateral triangle. Okay, and the method is easy. It's just a 3-step method. You don't have to do all that arguing that Euclid does in his book, so all this here is just totally unnecessary. You choose any point A and place the visualization of the distance. This is BC. This here isn't a straight line. It's a distance. It's a visualization denoting the distance BC, okay? So straight line is the shortest distance between B and C. That's what it means. Then you're not really constructing an equilateral triangle. You're representing the distance formed when three distinct points are joined, when the shortest distance between any two or three distinct points are joined together to form a complete path. That's and what we call that distance is called an equilateral triangle. Okay, so this little geometric object here that you see here is not a triangle. It's just a visualization. Okay, I'm stressing this because most of the morons in mainstream mathematics media do not understand these things, and I'm talking about math professors and math teachers. Okay, you cannot draw distances, you cannot plot points, okay? You cannot plot this point and you cannot draw this distance. That's absolute nonsense. And the last point is that you need a circle with center D, as you see there, and radius BC, okay? This radius. BC plus, radius BC plus the side of the equilateral triangle. And then, of course, obviously, it follows that this distance here will be equal to BC because the radius of circle D is equal to that distance plus one of the sides of the equilateral triangle. Okay, very simple proofs, very easy. That's all it meant. And so I'm going to leave you with that now. And I will probably continue with this sometime later. I don't know if I'll do maybe the next couple of videos or so on these propositions, and I'll let you study these in the meantime. So this is a new calculus channel, and I'm John Gabriel. Till next time, goodbye.